Is working on the room? Is it working online? Sound is okay. Yes. Thank you.
Now, people in Zoom land won't be able to have a chocolate covered chocolate donuts.
No, people in Zoom land cannot have.
You were in audio range, you can run down and grab your donut.
Cannot have chocolate covered donuts. Okay, this is.
Yeah.
This is the. This is the part that always gets me. Okay. I think the screen share is working.
Yes, it is.
Of course, LIDAR, your terminology would be chemical.
Correct. But they use it as light because not everybody knew what gamma was.
Yes. I don't use gamma. LI is the light.
That's the light they use those. Oh. No, no,
yeah. You don't want to find it.
And the way they use that is same thing as radar.
Hey, Jared. So this is the screen that's projecting, and this is the screen that is sharing.
Okay.
Okay. And you've got your chat here, and forwards, backwards.
Yep. Space bar.
Forwards, backwards, or errors.
And then
Notes are there.
Notes are there?
Mm-hmm.
Okay.
Oh no, those are not your notes.
No, those aren't my notes.
I lied.
It's only for the
okay.
yeah, the chat is
yeah.
I can
the chat's
pull
in
it
the way.
Yeah, I'll pull it up at the end. Because I don't need to.
You can get to the chat right there.
Yeah.
I just moved this bar so it wasn't on top of this.
No, that's fine.
Yeah. Whoever wants this.
Well, you can set it on the table for now. And you put it on the bottom.
Yeah, put it.
I get to say lots of embarrassing.
So he can get a job that makes more money than both of us? Hey, careful.
He will in about 3 years. Yeah, they already moved the section. Great. Because they'll be working. Yeah, I already, he told me I'm gonna get it. Yeah.
Guy comes talk to you, I'm like, flashing that. Oh, there's L.
There's L and.
There's like random variable. He was like an NC starter.
No, he was,
Yeah, his now mission on this, but
is, not supposed to.
I know it.
Yeah.
All the people on the bench.
Right.
An elephant or lips. Sure, my job. Well, this is all being recorded. Yeah, that's why I don't want to pick up this phone.
That's pretty good. Yeah.
Yeah.
Yeah, for
Copy anybody, don't have to want to grab it before we start.
for whatever reason, the news symbol didn't transfer from one of the.
It's not that good.
Yeah.
It's probably
Because it actually is new, not the.
Yes, I know.
Yeah. And it could be, but,
But when you do the new, it's an end.
oh. For Apple.
Right, it's being translated. Oh, the sympathy will make it.
Oh, yeah.
Okay. Well, it's 2 o'clock. Let me get the intro. Okay, welcome everybody. We're going to start. It's 2 o'clock. Today is the next to the last physics seminar, and we have a speaker who's got the Shaw Summer Fellowship Award last summer, and that's our most important and prestigious summer fellowship that we give. And the requirement of this Shaw Summer Fellowship Award is that the speaker has to talk about what they did in the summer. And it was a great honor to have Jared, which has been my student as both an undergraduate and now a graduate student, get that award and present this talk. Jared's one of these unusual overachievers. He actually was an undergraduate at both mechanical engineering and physics, got one of those double majors across colleges that we implemented some years ago, and he's been very successful at it. But instead of going off to a master's degree in engineering, he's doing a master's degree in physics. He's been working on my NASA grant, and he's been essential to that. But everyone who does a master's with me has to do some physics. And the physics has to be something not necessarily part of the NASA grant. He's doing a physics project that kind of interests him. And that is there a way to look at the directionality from the neutrino at both solar neutrinos as well as reactor antineutrinos? And he's concentrating on that. And of course, this is be the topic of his master's degree, which won't be defended for a while. But the research he's going to be talking about is the preliminary research he did to get this started as part of the Shaw Summer Fellowship for our graduate students. So please join me in welcoming Jared. Put that in pocket.
Check.
Yep.
Okay, can everybody hear me?
Yes.
Okay, so like Dr. Solomon said, I'm going to be talking about neutrino detection, specifically the reactor neutrinos or antineutrinos. And we decided to come up with this name of NUDAR. And that's going to be my topic of choice for my thesis. So let's see, that'll work. All right, so NUDAR, what is NUDAR? So it's getting its name from older technologies such as radar, which stands for radio detection and ranging, LiDAR, which is light detection and ranging. So naturally, we decided to come up with NUDAR, which will be neutrino detection and ranging. Where this difference is, so with radar and LiDAR, what actually happens is, radio wave is sent out, and we track how long it takes to come back to us. And that's what we can manipulate what objects are in that way. Same thing with the laser for LiDAR. It's for precision measurements. We shoot the laser at it and we come back. Neutrino or NUDAR, on the other hand, is slightly different. So as with its predecessors, it could have the ability to trace, track, locate, and possibly image. We're still working on that one. In some kind of capacity. It would be looking directly for electron antineutrinos or nu negative, which is a fermion or elementary particle created during nuclear fission. So basically what this is saying, instead of sending something out and waiting for a response to detect something, we are actually coming directly from the source. So it's a little bit of a different way, but it follows in with the detection and ranging. Okay. So before I get into the actual project, I want to give you a little bit of a background, a little bit of history on the radioactive decays and where neutrinos actually come from. So radioactivity was first discovered in 1896 by, I always screw up his name, Becquerel, within uranium. So that was first discovered by him, but it wasn't until 1899 that Rutherford separated the emissions into two separate groups based on penetration. So anybody that is a physics major, you understand that, you have alphas, betas, and I'll get to the gammas in a minute, but alphas are basically stopped with your skin, a sheet of paper, a small piece of aluminum, and alphas are stopped. So he separated those away from the ones that can penetrate, and we call those betas. The betas can penetrate to some degree, a lot further than the alphas. And then in 1900, Villard, who was, I believe, a French physicist, introduced what we know as gammas. The reason why we got alpha, betas, and gammas is because it's the first three letters of the Greek alphabet. So they just started going down the line. And afterwards, even though there are other particles, they just stopped naming them. We'd be going on forever. So that's kind of where the radioactivity starts, radiation detection starts. After that, we move into the early part of the 1900s, all the way up to 1930. Several scientists studied the beta decays in particular. Beta decays are essential when it comes to radioactive, especially fission decay. The consensus was that the kinetic energy distribution did not follow the laws of conservation of energy. So when we originally were discovering this, that we thought it was a two-body problem, that the decay just released an electron and that was it. That didn't solve the energy spectrum. So what we would normally want to see is, if it was just a two-body problem, would be a single peak. But when you study the actual distribution, it becomes a huge distribution and schematic of that energy, which means that there's something else there. We just can't see it. We don't recognize it. So everybody was a little bit confused on where that was coming from. So it was theorized that the distribution should have a single peak, like I said, and it wasn't until Pauli came along. And during 1930, Pauli was the first to postulate that if the principle of energy is to be conserved, if physics is to be standard across the board, beta decays need to be a three-body problem. There is something very funny about Pauli on this. He actually didn't want to go forth with this and look at it. The reason why is because he thought he'd be laughed at. So it wasn't until 1933 that Enrico Fermi came along and gave the first theory. In the first theory he developed for the beta decay, it consisted of what are now called four fermions, named after him. They're elementary particles. So we have the neutron, electron, proton, and the newly theorized neutrino. And that's the background of where all of this started. So we move on to the actual discovery. Like I said before, we weren't able to detect anything. Nobody actually theorized that we could detect it because there's no charge to it. So it wasn't until 1956 that the Cohen and Raines experiment, also known as Project Poltergeist, because like I said, they're looking for a ghost. And they conducted an experiment in 1956 at the Savannah River reactor. Both Cohen and Raines were scientists at Los Alamos. And originally the concept was that they were going to go to Nevada and set off a nuclear bomb and test it. Luckily, they decided against that. Some of their superiors decided against dropping a bomb in, yeah, oh yeah, it was, but they decided to go to the Savannah riverbed, which actually helped them. So it gave off way more what we call the neutrino flux. Now, flux is how much of the particle is going through your element per second. Okay, so we'll get into that a little bit later, but basically you have a cross section. Your cross section is the interaction of an element with another element. So in this case, an electron with a proton. Your flux is dependent on that. So they were right up against the reactor. They were 10 meters away from it. They sat outside of it. And their experiment, what it consisted of, basically 2 tanks of water, huge tanks that were over 100 kilotons, were sitting outside of it. And then there was another tank on each side. So they labeled it. So it's 5 tanks. And the other tank was consistent of scintillating material. The scintillating material is what caused the neutrino interaction. That's what the neutrino actually hit. And then they use cadmium chloride or CdCl2 as a dopant for neutron capture. Now, neutron capture is extremely important when it comes to neutrino detection. A lot of the things will come in, and we'll get into the Feynman diagrams in a little bit, but it comes in, it interacts with the proton, and it shoots off a positron. Well, a lot of things can do that. The neutron capture gives it another pulse, and it is timed. So for their experiment, it was 2.2 microseconds right after the neutron capture and another gamma. So we got a double pulse coincidence, which ensured that we actually had anti-neutrino or reactor neutrino. So current events or current experiments, like I said, we went from the very beginnings to what we're doing present day. Camland opened up in 2002. It's located in Japan, and it's surrounded by 53 reactors. They are all within 180 kilometers away. And this is specifically to measure more precisely neutrino oscillations. Daya Bay, which is also very similar to it, is opened up in China. It's 190 kilometers away from one reactor. And it is there to, again, do oscillations and see if they can get better numbers for the mixing angles, which the mixing angle is more of a matrix than anything. And then we come to the third one that I have on this list, which is very similar to what my project is doing. It's called Watchman, and it's under construction. It's in the United States. It is a mobile kiloton detector. So basically, they load up this big oil tanker truck, and they drive it up to reactors. And they are less than 100 kilometers away, so they want to be within 10 to 50, but they have gotten results all the way up to about 90 kilometers away. And they use it to detect nuclear materials. This is very important because Watchman is specifically for maintaining reactors to make sure no meltdowns are happening, none of the material is going off when it shouldn't be, everything like that. So it's very similar in concept to my project. So I included it, but those are the 3 main experiments that are going on for reactor neutrinos. There are several more, and several more have been happening. Also with other experiments such as Nova or New Sol or stuff like that, we take our technologies for neutrinos that we use for reactor neutrinos and see if we can incorporate some of the same things. So the exploratory concepts of NUDAR. What is NUDAR going to do? What do we think it can happen? So can we be able to detect reactor neutrinos while we're moving? So far, all of these reactors are deep underground, or like in the case of Watchmen, they pull right up to the reactor and they just sit there and they wait. Okay, that's fine, but are we able to move around a source and still be able to detect it? Now, the key to this, like I said earlier, is the flux high enough to indicate events or to show that our events are happening? And we'll get into the flux in a second. But that's one of the key concepts of what is NUDAR. Can we point? Can pointing occur? Is it possible to point to a nuclear source? What is the minimum power of the source for detection? So nuclear reactors are about, on average, 3 gigawatts of energy. And now we can detect them from, about 200 kilometers away, which is decent. We can detect them from further, but the further we go, the less events we get, the accuracy goes down. But what we can do is, so what we can do is, what if we turn that into something that is moving, like a nuclear submarine? Okay, now a nuclear submarine compared to a reactor is only 200 megawatts on average. So we're going down quite a bit. Now, are we able to detect that? How far away do we have to be to detect that? And can we use some kind of triangulation method for positioning? Now, what I mean by that is if I have more than one detector out there, and it will give me an array of, yeah, it's in this general direction. Okay. If I have a second and third, it'll give me different angles and a different directionality. That means wherever they cross, that source has to be in that area. The more accurate we can get, the closer we can get, the more accurate the detection will be. So that's one of the concepts that we're looking into. What we need to do for the size of the detector. So basically, can I use the detector on, say, a ship? Can I use it on an aircraft, or can I use it on a low orbiting spacecraft? So the size of my detector is also key. Again, it goes back to the flux. I need to be able to have so many particles per second reach my detector. And my detector is really, really small, say like New Souls, it's not going to get a lot. Now, if I have something as big as a tanker ship, I might be able to get some. My goal is to be able to see probably about, from best estimates, is 3 neutrinos per minute from my simulations. And if I can do that from multiple sources on a moving target while I'm also moving, I'll be able to have directionality, better angular resolution, and be able to pinpoint where the location of the source is. What does this mean? Implications of NUDAR. It could create an easy detection of nuclear reactors and install monitoring systems, just kind of like Watchmen, but on a more mobile, more global source. Ensures regulation of fissile materials are met, and not only within the United States, but other locations around the world. And it also increases defense capabilities. If flux is great enough, it is possible to determine nuclear-powered vessels such as other submarines or other aircraft. And that's kind of the key to this. I am very much focused on the defense side of this project. It increases the monitoring of nuclear detonations. I can tell you if there are other nuclear vessels around and if they are somewhere they're not supposed to be, basically. So that's kind of the implications of NUDAR and what we expect we can do. Now into the science. That was all the background. That's all the information that we need to get into the actual science portion of this presentation. First and foremost, we need to start with the interaction. Interaction, this is within the nuclear reactor. So this is within the nuclear source. We have what's called an electron emission or a beta minus decay. And this is what stumped scientists for so many years. It's a weak force, weak nuclear force converts a nucleus to a nucleus of atomic number increasing by 1. This is one of the ways to do it. So basically, it's just going to increase your proton, and then it expels electron and the electron neutrino. Now, everything within the nuclear reactor is going to stay within the nuclear reactor. Not many things can go through it. They're aligned with lead, everything like that, but the neutrino can. The neutrino doesn't interact with very many things, so it passes through the reactor and it goes out into the world. Another way we can do it is through a free neutron decay into a proton. Unstable neutrons outside of the nucleus. It has a half-life of about 10 minutes, and it goes from the decays into a proton, electron, and antineutrino. And that's what this Feynman diagram is on the top of the screen over here. And you can see how the nuclear reaction actually occurs. Energy is shared between the electron and the reactor neutrino. This is what Fermi decided, theorized about, and Cohen and Raines proved. So within a single reaction, either particle can have most of the energy. But when you have a large number of decays, such as a reactor or some kind of fuel source, the reactor neutrino carries 2/3 of all the energy. So that's 2/3 of all the energy that is happening, that is being expelled from the neutron decaying into a proton, goes into the reactor neutrino. So that's the first part of it. So we have the neutrino out into the real world. Now, what do we do with it? So inside of our detector, we have what's called inverse beta decay. So we're basically going exactly the opposite way. I joke with my other colleagues because I'm turning a neutron into a neutron to detect a neutrino. It's very confusing, and it can be a little bit stubborn at times to get this down. But the neutrino comes in directly from the source, and it interacts with the proton. This is our target. This is our scintillator, like Cohen and Raines use, and it interacts with that proton, and it turns into an electron, a positron and a neutron. That positron will go and annihilate almost immediately. And as soon as that does, it releases a burst of gamma. The gamma within our detector gives off light, and we are able to detect that light. And like I said earlier, the double coincidence is when the neutron captures. For my experiment, we're probably going to use gadolinium. That seems like the best fit for right now for the neutron capture. And it is 200 to 300 microseconds after that first burst of gamma light that the neutron captures, and it releases 3 particles that are up to 8 MeV, and we can detect that. And that gives us our double coincidence because it gives us another pulse of light. And I do have a couple of equations for the flash of light here for what's visible, what's not visible. But anything over the 5 MeV will be visible. And then, yeah, we go into the neutron capture and it'll shoot that one off. Decay chain. So this is where I started. This is where my project started. So there are 6 elements that I specifically looked at: 1 thorium, then uranium, then plutonium. And this is an example of one of the decay chains. This first picture that you see is the very nice one. This is the one that everybody sees. This is the main decay chain, which is the probability. It's 92% possible that this decay chain actually happens. The other one, which is going to be very hard to read because it is so big, is the actual decay chain. This is everything: the alphas, the betas, the gammas. Well, the reason why I included this is because during my simulations, you have to include the alphas and the gammas because they can turn into betas eventually down the line. If you can see it, it might be a little hard on the screen here, but there's a bolded white line, and that is the main decay chain, which is presented on the other side. But the possibility of all this happening, there is a possibility of all this happening and releasing energy. So we accounted for it. To my simulations, this is the next step in my process. I use JONT4, which is geometry and tracking. So I did simulations of all nuclear decay chains for 6 total isotopes. It was well over 3,000 decay chains. It took quite a while to even run this, to get graphs and get the events per energy. I created histograms, which I will show you in a second. And then after that, what I did is I created this layered detector. So once that positron annihilates, the neutrino comes in, hits the proton, and creates that positron. Well, the positron is going to have energy. And a single detector isn't necessarily going to pick it up. It could always shoot through it. The neutron doesn't have to capture right off the bat. So we created, between Dr. Salome and I, we created this idea for a detector that has layers. This detector is made up of 5 layers of gadolinium and 4 layers of our scintillator. So we are able to detect and trace. Each one of these scintillators will have fiber optic lines going through it, and they're basically a cell. This one happens to be 50 centimeters wide. The scintillator is 2.5 centimeters thick. The gadolinium is 0.25 centimeters thick, but 50 centimeters wide. So what happens is when it interacts, it'll shoot off, and that fiber optic line will light up. And then it goes into the next scintillator, and it'll light up. And then it goes into the next scintillator, and it'll light up. That gives me a place and a location and kind of a trace where I can trace that positron back. Same thing with the gamma or the neutron. It'll release those final state gammas, and they'll shoot off, and I'll be able to see where that happened within the next scintillator. And I'll be able to trace those back to the neutron. I'll be able to trace the positron back and the neutron back to the positron, and that is the neutrino. And neutrinos go straight. So whatever direction that is where the source came from. This is what gives me my angle. And this all depends on how far away I am from the target or from the source. My next simulation was Genie. This is specifically a neutrino Monte Carlo generator. It was used in determining the best scintillating target. So there's plenty of plastic scintillators out there. Every experiment uses several different ones. Nova uses mineral oil. We use a gag crystal. Cohen and Rains used water because they wanted to hit the protons on that. What is actually the best one that we can use? So Genie helped me simulate this. And it was a lot of long hours and a lot of long simulations. I ended up analyzing over 317 isotopes. So anything that you could possibly create a cross section, I simulated. And I'll get to that data here in a second, but these simulations took weeks, 500, 600 hours at times to simulate all of this. This is what I got from Jayon. This is from my simulations of just the decay chain and energy. So we have thorium-232. This is 99.9% natural. This is the one that's found in nature. It is a fertile material, meaning that it can be converted into fissile material, which actually gives off the nuclear reaction. It becomes a fertile material by thermal neutrons and neutron absorption and nuclei conversions. This chain is also it also happens through the decay of uranium-233. So uranium-233, one of the chains that it can decay into is this thorium. As you can see from the graph, the one that we have that is the bigger graph here on the left is the full energy spectrum. Now, a lot of this is all in MeV. A lot of this is in the keV range. That's great, and there's a lot of energy there. The problem is that we cannot detect in the keV range. Our threshold for detection is 1.806 MeVs for neutrino, reactor neutrino or a regular neutrino. The reason why is the mass difference. So I made a cut scale of it, and as you can see, my wonderful energies that I have got trimmed down to very few energies and very few reactions. These simulations were run ran at 100 million events. So I shot 100 million particles at this, and it shot out how many events will I get. So this one ended up being just about 40 million or 400 million events per 100 million decays. The next one that I did was uranium-233. As I mentioned, it can decay into thorium, but it has its own separate ones as well. This is a fissile material, and it can be used for both reactors, subs, nuclear powered vessels, and weapons. As you can see, again, my cut scale on this, very few, so that makes this almost improbable to detect for this one particular, but because of the thorium, I am able to detect some of the uranium 233. Next one that I simulated was uranium-235. This is 0.72% natural. It is a fissile material, but as you can see on my cut scale here, that hardly any events actually triggered past that 1.8 MeV, meaning that this could be up to statistical error on this one. So this one, it would be very, very difficult to detect. It's also not commonly used. Uranium-238, this is one that's mostly used worldwide. This is 99% of the natural uranium. It's fertile material, and it can transform into plutonium-239. As you can see from the cut, this is one of my highest energies. This is one of my highest rates. This is the one that I'm looking for in particular. Not that I can dictate which source I'm at yet. That might be a project for the future, detecting which source it came from, what type of source it came from. I'm looking for any source right now, but if we want to specifically make a detector that only detects that type of source, this would be one of the elements that we could do that for. I get into the plutonium-238. It's fissile. It's also a radionuclide, meaning that it's a very unstable product of nuclear fission. It was first synthesized by bombarding uranium-238 with deuterons, which created neptunium, and through beta decay, created the plutonium-238. This one can be used in reactors and also with weapons. But if you look, and I'll go back real quick, uranium and the plutonium here, their graphs are almost identical. Here's the uranium-238, there's the plutonium. The only difference is the top shelf, which is the decay from the uranium in a different way. Plutonium-239, it's 0.8% in abundance. It's fissile. It can be used for weapons and for reactors, but again, with the events, this becomes almost statistically impossible to detect. And then my target solution. So next goes into my Genie simulations. Like I said, it's 317 isotopes have been put through several different models and modified, standard models and modified models. I have over 28 models that I ran each isotope through. I ran several events for it, and I ended up with over 8 million lines of data that I have to analyze. So we're currently doing that. Haven't finished that one yet. Hopefully I can create a program that does it a little quicker, but we're working on it. Then this is kind of the results of that simulation. I did it for hydrogen 1, hydrogen 2, helium 1, 2, and 3. So I have 5 isotopes that I created a spreadsheet for that I decided to look for which cross-section is best. So over 25 models, and like I said, I did all those isotopes. Lower energy regimes are very difficult to simulate. So as seen in the decay chains, my range is about 1.8 to about 5 MeV. Once I put them in graphs, Genie likes to work in GeV instead of MeV. And the lowest they will go is 0.15, which is 150, 140 MeV. So what I had to do is extrapolate from there using a power series, because it should follow the power series. And these graphs show my power series versus the actual cross-sectional data that I received. As you can see, models 2 and 9 ended up being almost identical to what the cross-section extrapolated, almost being identical to the actual simulated cross-section. Models 21 and model 23 are the ones that don't look as great, but actually are better contenders. For the future going forward, I think I'm going to actually choose helium-3 as my particle to use. And I will show you here. This is my Genie output. So this is the raw data that I had extrapolated down, and these are 3 different sections of that data, and it gives me the cross section. Now, if you can see with models 2 and 9, they looked great, but if we look at their cross section at 1 MeV, which is a little bit low, but as you know, my energy was low. Cross section of 10 to the 104th, which makes it impossible to detect. Cohen and Rain's experiment was 10 to the 44th. And that's the place where I need to be for detection. That's what all the neutrino detectors are working at, either 44, 46, or 48. Again, with model 9, -87. The reason why I put model 21 and 23, which is the hydrogen 1 and helium-3, is their cross sections actually look great. My cross section for 1 MeV is -10 to the -44 for the hydrogen, and then 10 to the -60 for the helium. Now, again, this program wasn't specifically designed for low energy. Like I said, they work in the JEV regime. So this data is actually not, there's a very high systematical error in this data just because the program wasn't built for that. So there are other programs that I'm probably going to use and try to model this and see if I can get a better number, or if I get consistent numbers. If I get consistent numbers, I will use H1 as in model 21. But from other research that I've done, helium-3 looks like one of the best outputs for this, for the cross section. My goals and future work. So I want to finish analyzing the cross-section data to best fit the target element for reactor-neutrino interaction. And then I want to simulate the final state particles and energy ranges. So not only the gammas from the final state, but there should be other things that pop off that I need to be able to trace back to the neutron capture and back to the positron and proton neutrino interaction. Like I said, I want to use other reactor neutrino generators, simulate in other programs to ensure I have what is the standard, what we can use, what is the best working model for this. And then I go into the JEONT simulations. I incorporate what I get from the other neutrino generators into JEONT, which is where I built my frame, where I built my actual detector, and I want to see how my detector actually works with the actual particles models and see if I can trace it. So I'm going to incorporate it into my shield design, insert tracing and tracking mechanisms such as fiber optic lines into a design such as a block detector. So that detector, while the one that I showed is one single piece, imagine you have several of those lined up and all throughout, say, a ship. We have several of those everywhere so that we can get it from any angle, no matter where the source is coming from, no matter which direction the ship is facing. We are able to detect it from hopefully a 360-degree place. And then this is to indicate the paths of the particles have taken and then trace back to the original source. I want to be able to manipulate detector angles to explore the angle of resolution problem. So basically what I mean by that is, what if a neutrino comes in and hits the top of one of my detectors instead of a faceplate of my detector? Am I still able to detect it? Does it go 1 or 2, or does it just scatter off? Am I able to detect it from any angle at any time and get a resolution from it? And then I also want to design this goes back to my engineering. I want to be able to design a detector in a way that it's a standalone in itself. So say the ship is moving one direction, we pick up a neutrino detection. I want to be able to move that detector without moving the ship. I want to have some kind of mechanism that rotates around within the ship on a standalone, so I can point it in any direction at any given time to hit a focal point of where the neutrino came from. Say I did get just a little blip on one of the sides of my detectors. Well, I want to be able to move that without taking the ship off course, or moving it, causing a long delay. That's kind of my future vision for this project. And then in conclusion, so what does this actually do? So it increases our understanding of lower energy reactor neutrinos and creates advancements not only in particle physics, but also creates new innovative technologies to implement detection processes. Establish a better cross-section and flux spectrum. That is the major hangup in anti-neutrino research right now, is that the cross-section is so high. And it varies depending on the materials that you're using, how far away you are, well, for the flux, how far away you are. But if we can come up with a better understanding of it, we'd be able to implement better science behind it. And then I also want to understand if utilize pointing capabilities of such a detector. Am I able to point? Am I able to detect? Am I able to basically use it as NUDAR, but radar, and pinpoint a location that the source is, even if that source is moving? I want to be able to move with it. I want to be able to take 3 detectors around and give you a area that, hey, it is right here. It also has the ability to not only increase nuclear power monitoring, but also, as you can imagine, increase defense capabilities. And what this really means is, if this works and we're able to figure this out, it minimizes the risk of nuclear weapons and creates a much needed nuclear deterrent. That's my presentation.
Okay, we have time for questions and discussion.
Yep.
Well, let me just first, this is an exploratory idea. And then, you have these plates in layers of some neutron and neutrino sensitive material. Maybe some simulator that capture the free neutron. And okay, an object you might be certain might easily be somewhere in the Western Pacific Ocean, maybe the Eastern Pacific Ocean. It could easily have 2 sources. It could have a nuclear reactor powering away. And you said 200 megawatts, the most nuclear class long system self-circuit.
Yes. Correct.
But they also have then all those plutonium bombs.
Correct.
So you want to find.
Yep.
And they can be a source of emissions of neutrinos of specific. And you said something about 3 per minute. I'd be happy with 3 events per day.
Right.
That would be enough if you had like 2 ships and they were detecting 3 events per day. Don't forget the ships we're talking about are the size of oil.
Yeah, they're huge. Yeah, three per minute is best scenario. 3 per day, we can still make it work. Yes, but yeah, I'd prefer somewhere, 1 or 2 an hour or something like that. Because they're moving, we're moving, it makes it a little more difficult. But yes, 3 per day will work.
I'm just trying to bring this out that it doesn't have to be. It could be a much smaller detector.
Mhm.
You can even have one at station.
Correct. Correct. One of the right. One of the ideas that I was floating around was that we actually sink a detector off our coast and basically create a barrier that we're able to detect. And we put, 1 in Alaska, 1 in California, 1 in Hawaii. And hopefully that's strong enough that we get enough neutrino interactions that we can detect it in between that area. Yeah, that one cannot rotate. The ship can rotate, but I also do want to see if I can make the detector rotate too. And the reason for that is not necessarily for the ships, but if this idea goes forward, if we can put this on an aircraft, then we need to be able to rotate because the aircraft's moving way too fast, and we need to be able to pick it up and point directly to it. Same thing with the low orbiting satellite. So that's far off in the future, but that's where I would like to see it go. Yep. Correct. Yes. Yeah, and that's basically where I'm at now. I'm going to, like I said, I'm going to simulate a single element and see how big I have to be, and how far away I can get. And that's where I'll go. And then eventually, hopefully further on in my career, be able to optimize this. Yes, sir. Yes, sir.
There's natural radioactive. And there's obviously how do you sort of separate what you want to act from obviously one generated?
Well, the neutrino is only caused by, the reactor neutrino is only caused by fission beta decays. There are ways that we can cancel out the noise, just like solar neutrinos, we can cancel those out. There are ways that we can put, like my colleague and I were talking, maybe a magnetic field around something where we can kind of cancel out some of the noise, but that's, haven't gotten quite that far yet, but that's kind of the ideas. Right.
Not something, if you change the angle of the ship, these planes would all be pointing sideways.
Correct.
If you change the angle of the ship and the signal goes away, you come back and the signal goes up.
Yeah.
This is in slow motion.
Correct.
If you're only looking for like you said, 1 per hour.
Right.
Really.
Yes.
But it's something that third has started, and that you'll be hearing like the preliminary results of the defensive master secret.
Yes.
It's just an idea to see if we could, what we could figure out, if we figure out any
Correct.
things there.
Thank you.
Coffee and donuts, everybody, and the next week, the last one of the week. It's 11 minutes. Sorting things out.
Yeah, right now with all that, especially on baby stuff.
Any questions from anybody on Zoom? Doesn't look like it. Okay, thank you.